right. Good morning. Welcome back. Hope you enjoyed your break. I know I did. And before we start, I got a couple of emails about the the exam and the file submission questions. So what I'm going to do is open a link in Blackboard because the email send it to my email is just going to get buried. So I'll open up an assignment link in the same folder with the exam, and that way you can just turn it in like that. That'll be easier than having to sift through my email. I'm gonna put that in the chat too for people who come in a little bit later.
Dr. Russell, you talking about the 2 questions that we had to upload on the test?
Yes.
If we already if it already worked for us.
Yeah, if it worked, that's fine.
Oh, okay.
Yeah, it's only for people who couldn't upload them. But it's good that was only a couple. I don't know why it would have not have worked, but it is what it is.
I'm gonna get all the code.
Dr. Russell, you said where's the link for it?
Say again?
You said where's the link?
No. I said I'm gonna add one.
Oh, okay, got it.
Yeah, it's only if you have problems uploading the file submission problems though. Yeah, if you uploaded them when you took your test, it's fine.
Oh, okay, got it.
Yeah, no, there's no need to upload it again. All right, we're gonna go ahead and get started. We're still talking about organometallics, so we're gonna pick that back up. Come on. There we go. All right. So we left off talking about organometallics. We talked about how to make them. We talked about their connection or their link to alkyl halides, which is how most of our organometallics are synthesized from a alkyl halide start material. And we talked about how to make granules, also how to make Gilman reagents. So here we're just working through some problems with these organometallics. And then we're also going to introduce today the addition of organometallics to carbonyls. So that's another type of reaction generally used for the synthesis of alcohols. So we're going to talk about that. But first, we're going to finish up these problems here with the coupling reactions. All right, so let's go to the bottom reaction here, right? And again, with these reactions, we are identifying CM and RX, and we're trying to make a bond between C and R. That's the end goal of the reaction. Right, so here we want CR, right? So in that fourth reaction right here, right, which one of those is CM? What is M? What does that represent? Let's jog your memory, because I know it's been a long weekend.
A metal.
Metal, good. So over here you can see that magnesium and the metals in this case, we've only discussed two organometallics, right? We talked about granules, we talked about Gilman reagents. So your metal is either going to be copper or magnesium, right? Those are not it's not limited to that, but for the scope of this class, those are the organometallics that we've discussed. So magnesium is here, and then we said an organometallic has a covalent bond to a metal between a metal and carbon. So here's my carbon right here, right? So this on this side, this is CM, right? And it's that carbon that's going to end up in a bond with the carbon of the alkyl halide, right? So over here, you can see the RX, right? You find your halogen or your leaving group, and the carbon is bonded to. So that's going to be RX. It's that simple. And then we want to put these two carbons together in the product. And again, we're doing this in aprotic solvent at low temperature, always. Right? So what would that product look like? Anybody want to annotate the screen and draw it in? No takers on a Wednesday.
You want us to tell you what to put? Or you want us to, what did you ask?
I was asking if somebody wanted to annotate it and draw it in. Or you could tell me if you know, that's fine too.
Can I tell you?
Go ahead.
Okay, so the purpose is to get the carbons together, right?
Mm-hmm.
Okay, so it would be magnesium chloride.
Okay, we'll take that. The bromine is still there too. All right.
And then it's just a carbon-carbon bond, right? Or no?
Yeah. No, you're right.
Oh.
We want to make that carbon-carbon bond, but I just want to make sure we know where it's located. So I'm gonna put this in here. That's my bond. The reason I'm drawing the bond first is because it's very tempting to fuse the two carbons together, and that's not the case. So I'm going to draw this like that. All right. And then on the other side, I'm going to draw what was bonded to that carbon like that. And if you look right here, these are your two carbons, right, that came from the start material. It's very tempting to just fuse them together, like to not draw the bond and just draw it like this. But that would be incorrect.
So it would make sense to draw the bond first and then draw the two sides like you just did?
Yeah, if that's a way to simplify it, yes.
Okay.
Mm-hmm. Let me move this down here. I gotta fix my note first though. All right. And what organometallic is that with the magnesium?
The
Anybody?
Grenier.
It's a Grenier. All right, it's a Grenier reagent. All right, let's go up top, because with the Gilman, again, it's a little bit more, it's not complicated, but it's a little bit more to wade through, because as you can see, let me go back up to the where we first made it and kind of recap that page. Yeah. So you can see with the Gilman, when we make it, you actually start with 2 equivalents of organolithium. You react that with copper iodide and ether, or copper iodide, sorry, and ether, and you end up with the Gilman reagent. Right? It does organometallic coupling just like a Grenier. The difference is that when you couple, only one of the groups that's attached to it is going to couple to your alkyl halide. All right, so let's go back down to here. And we could actually, I'm going to draw this out over here. So this is going to look like this. So you got copper, and then a 1, 2, 3 carbon chain. That's going to look like that. Right? Remember, lithium is positive and copper is negative. Right? But when you react that with an alkyl halide or some other group that's capable of doing coupling, only one of these is going to transfer. Right? So let me change the color of one of them. All right. So this is what that Gilman looks like. That's why it has a subscripted 2, because there are 2 of those groups attached to copper. All right. So if I take that and react it with this, where is CM?
Next to the I.
Say that again.
Is it with the I? Iodine?
No, that's actually going to be RX, right? Because the iodine is my X, and then because X is it's a generic descriptor for a halogen, but we also using it in this case to describe any leaving group, because it doesn't always have to be a halogen. All right, so that's my RX. So over here, I find my metal, right? Remember, the M is for metal. So this is M and that's C. So it's going to be this carbon right here and this carbon right here that are going to couple together. Are y'all following that? Because that's the carbon that's bound to the metal on the other side. And let me move this actually.
Okay, Dr. Russell, you lost me. So can you explain why only one is coupling again? I missed that part.
So the way the mechanism is kind of debated, but the way it works is, in this case, it's probably more like a substitution followed by what we call like a insertion and then an elimination. And so with the copper, when it adds to, when that copper adds, let me just show you over here. And I'm going to put just R1 and R2. And I'm going to call that R3. Right, so when the copper adds here and forces out the halogen, So you end up with copper, R3, R1, and then R2 plus the lithium salt of whatever that halogen is, right? And then, right, you can do in this case what we call reductive elimination, which is beyond the scope of the class. But the point is that I'm able to shift this here and then these electrons back to copper, right? And so then I end up with a bond between R2 and R3 plus copper R1 plus that lithium salt. And so this now is dead, right? It can't do another transfer. So it's dead. And this is my product that I wanted. Right, so what you end up with is a copper salt or a copper species that is no longer active, right? What made it active was right here. You see how it has this lone pair on copper? That's what made it active. But once that copper is stabilized by getting rid of, you know, a pair of electrons and now the charge going to zero or becoming neutral is no longer active. So it can't do anything with that second group that's attached to it. Right, so anytime you use a Gilman, you're only going to transfer one of the two groups attached to it.
Okay, thank you.
That's a great question, by the way. I'm gonna cut this out and put it on a separate page so that
garage door.
you watch it cut that beat. I'm gonna cut that out and put it on a blank page back here. Let's see right quick. That way you can look at it later if you want, if you go back and look at the notes.
Dr. Russell,
Go ahead.
what atom does R stand for, or does that stand for a group?
Well, in this case, for what we're looking at, the R is a copper, right? It's R is like a generic descriptor. I'm sorry, not copper, carbon. So R is like a generic descriptor for like carbon functional groups. So in this case, it's the R group, where the R is representative of this carbon right here. Right, but in general, it's everything attached to that carbon, but that's the carbon that's going to be participating in the reaction. So we use R like it's just a generic way of describing what's attached to the halogen, which is really all of this back here, right? But the only atom we're concerned with in the mechanism and for the reaction is the carbon.
Okay, understood.
Mm-hmm. All right, so what are we doing over here? Like, what's going to happen? How am I going to get C and R together? All right, so I'm just going to draw the bond. So on one side of that bond, I have this carbon, and on the other side, I have a carbon right here. So on this carbon, I have that. Is that right? Now, what am I trying to attach? Or what should be attached after the reaction takes place?
Is it everything on the right side, like that carbon that was attached to the copper?
This one right here, right? That was in that one in that 3-carbon chain. Is that right?
Yes.
Mhm. And then what's left over is lithium iodide. Let me write that in. But this is all trash, right? All side products that I don't keep. Right? That's what's left over. And this is unreactive. Right? That's why a lot of times when Gilman reagents are used, they'll stick 2 groups on there, but one of them will be what they call a dummy ligand, like that they don't care about losing, because this is really highly simplified. But Gilman's, you can put really complex fragments you can attach to that copper. And when you do that, you don't want to put 2 of those on there that you might have spent, 3 or 4 days synthesizing just to put it on copper. So what you'll do is you'll take the copper and add your fragment, and then for the second ligand, you'll add in like a dummy ligand, like an alkyne or something like that. So you'll end up with something that looks like this, where you have, this can be anything. This is dummy. And then down here, you might have some very complex, chiral species, something like this, that you want to couple with, another fragment.
So
Go ahead.
what was the reason for, because I know like the lithium and the copper were together.
Mm-hmm.
And so we separate the lithium and copper and add the iodine to the lithium.
Yeah, because when let's go back to, let me just show you here, right? This is eventually going to leave, right?
Right.
And when it leaves, it's leaving with a pair of electrons, so it's going to become I minus,
Uh-huh.
like that. And then over here, lithium is positive. So it's just going to form a salt with the iodine.
Okay.
Mhm. Good question. All right, other questions about that? Let me put some more context down here. So you usually make it with like one, what they call, again, a dummy ligand. Go ahead, Quinetta.
Does it matter like which side that you put?
No,
Okay.
no, both before the reaction, both of those groups that are attached to copper are equally susceptible to reaction. So it doesn't matter.
Okay, thank you.
Is that what you were asking?
I think so.
Okay. Yeah, it doesn't matter. All right. So let's look up, let me see. I need to move something. See if I can move this. All right, so let's do the next question, which is, asking how to make this. So what would this give you if I took 2 equivalents or 2 moles of organolithium and reacted it with copper iodide? What would I get?
A Gilman reagent.
That's the way to synthesize a Gilman reagent. That's exactly right. All right. So what would it look like? I'm gonna change the color of it. You know you're gonna have copper, is that right? It's gonna have a negative charge. And then you'll have lithium ionically attracted to it. And then on that copper, what am I gonna have?
Does the
A lot.
copper like always? I know last time we drew it, it had like those two possible chains.
Yeah. So these chains right here are both gonna be, since we have 2 moles of it, we're gonna get 2 of those groups attached to copper. So it's gonna look like, not like that, like this. So that's one of them, and then the other would look like that, right? I'm gonna put both of them on there. And you can see it's the same thing right there, 3 carbons here. Well, 4 carbons, but, and then over here it's the same thing. You have the same 4 carbons. And the stoichiometry means that I'm gonna have 2 of those groups attached to copper. All right. Questions about any of these reactions that we've looked at?
Do you end up with lithium iodide in the end too?
Not yes. One of the lithiums will indeed make a bond or be a salt, make a salt with iodide. Yes, because you have 2 organolithiums. So one of the lithiums ends up ionically attracted to copper, and the other ends up with the iodide. Yes, great question.
So whenever there's copper, it has to be at least like 2 moles.
You mean to make the Gilman?
Yeah.
Yes. Yeah, you have to use 2 equivalents. Yep, you have to, in order to make a Gilman, you have to have 2 equivalents of an organolithium species to react with copper iodide. All right, and it's up here also when we first started talking about it. Right, we talked about how to make the organolithium as well as how to make the Gilman. All right, other questions about these problems right here? All right, let's keep trucking then. There are no other questions about that. Let's talk about addition to carbonyls. Right, this is still under the same umbrella. Spell. right? So we started out under this umbrella of the talking about how to make and how to use. Now we're talking about how to use alkyl halides, and we've talked about how to use them for organometallic synthesis. And now we're going to talk about addition of organometallics to carbonyls. I'm going to abbreviate organometallics as just OM. Right, and we're talking about this in the context of alcohol synthesis, right? Because that's your major product when you add an organometallic to a carbonyl. I have in the video, I think I sent this video out already, dealing with the addition, right? I have like 2 mnemonics to help you remember what happens. So a granular plus an aldehyde or a ketone will give you an alcohol. And if you take, now with the esters, it's a little bit different. So with a granular, if you add it to an ester, it's going to equal a ketone. But if you take 2 granulars and add them to an ester, then it's going to equal an alcohol. So we'll come back to all that. But let's look at this first example right here. And it has the mechanism and all this stuff down here. Right, so you can see here, I'm starting out with an aldehyde. Right, and I'm going to keep this in the back of my mind. A granular plus an aldehyde or a ketone equals an alcohol. All right, so with the aldehyde, I'm going to react it with a granular, and then I'm going to quench it. This second step in this reaction is what we call a quench step. All of these reactions have to have a quench step. And the reason why you have that quench step is you need to protonate oxygen to get an alcohol. All right. So if you look at the product, you can see right here that it's this oxygen here that got turned into an alcohol. And it's this group right here that got added to your carbonyl, right? So you have a new bond between these 2 carbons, this one and this one. You can see that right here. All right, so you got a new carbon-carbon bond and a new alcohol functional group. Right, so all of these reactions are going to be considered addition reactions. Right, anytime you add to a carbonyl, it's an addition. Right, and it is you cannot do a substitution on a carbonyl because it's sp2. What you can do is do an addition followed by an elimination, which we're going to see when we get to the ester additions, that you can do addition followed by elimination. All right, so you can see what the product is. You took the aldehyde, you reacted with a granular, and then you quenched the intermediate that you're going to get with a proton source. So H plus, let me just go ahead and clarify that because I always get a lot of questions about this. So this can be HCl. Normally it'll be a weak acid, but it can be HCl. It can be ammonium chloride, which is an acid. It's not an acid, it's a weak acid, but it is acidic because it's the source of H plus. It can be acetic acid. I'm gonna write it how you'll see it. Right, so H plus is just a general descriptor for some type of acid. So don't get hung up on that part. All right, what you can do to help yourself remember and to not freak out when you see H plus is just pick an acid. Just use HCl every time. If that bothers you, just use HCl every time, and that works. All right, so let's look at the mechanism. And you can see down here, again, let's go back to our initial conversation about organometallics, right? They are nucleophiles, where the bond between the carbon and the metal is polarized towards carbon. So the dipole is going this way. So that means carbon is partially negative, and then the metal partially positive, right? So we know that. So that's how we know that how the organometallic is going to react, how the granite is going to react. That's how we know how a Gilman is going to react, because by nature it's nucleophilic. So it's my nucleophile. All that stuff, again, that's part one stuff. So hopefully it's not off-putting to you to hear it now because you've already heard it before, right? So that's my nucleophile, and then my carbonyl, 99% of the time, unless you put some type of proton source around it that oxygen attacks, my carbonyl 99% of the time is going to be an electrophile. Right, and there's a reason for that. Everything goes back, you're talking about polar reactions, everything goes back to dipoles. That's how we know where reactions take place, because of charges, right? So the carbonyl itself has a dipole in the direction of oxygen. So that makes the carbon partially positive, it makes oxygen partially negative. So you got a partially negative carbon over here. That's a nucleophile that's seeking out an electrophile. So within the electrophile, that's the site that the nucleophile is going to attack. So that's why the arrows are drawn the way that they are. All right, so you can see that this is coming here. Like so, that's going to attack that. It's not going to look like that in real life. That's my way of illustrating it here. And then this is coming here. Anytime you attack a carbonyl, you have to break the pi bond between carbon and oxygen. All right. And then you end up with this intermediate. And that is what gets protonated, because oxygen, let me see if I can edit this. Actually, you know what? I got a better solution. Oh, not that much. I'm too overzealous with the pen. Hold up. I just want to take this off so I can show you. That the oxygen has lone pairs on it. And it's negative. And then the magnesium has a +1 charge, so it's just hanging out. It's really a salt. Like that. All right. So that's what the intermediate looks like. It's really a magnesium oxygen ionic bond. right? And so when you add in H plus, let's just say, for instance, what do y'all want to use? You want to use HCl? Is that okay? Because I
We
want to
actually-
show you the whole thing without, leaving anything out, so you don't get confused. Let's just use HCl. It's going to be HCl like that. And so oxygen is going to attack that. And obviously you're going to lose the chlorine. All right. So you end up with the alcohol. You can see that, right? But you're also going to end up with the magnesium. Right? Being bound to whatever the counter ion is or the conjugate base is of that acid. So in this case, it's chlorine. Right? But at the end of the day, none of this stuff matters, right? All of this is trash. When you do your workup, which is when you separate out the organic from the aqueous in a separatory funnel, all this magnesium, salts, and all that stuff is going into waste. The only thing you care about is the product. Right? Normally at the end of a reaction, what you'll do is you'll take the reaction mixture, drop it in, pour it into a sep funnel. I've never seen a sep funnel. I don't think we use those in organic lab. I'm gonna illustrate it. I used to be able to draw back in the day. So you got a separatory funnel right here, and it's got a little stopcock on the side that you can turn, open, and close it. And you'll add in basically your two layers. So you'll have your organic layer here. You'll have your aqueous. Let me fix that up. Still went out. Right, and you'll have your aqueous layer here. What you do is end up doing something very rudimentary. Shake the flask up and let the layers settle, let them separate, and then you drain off the aqueous, depending on what you're working it up with. So you're going to work these reactions up. So all of this stuff right here is going to end up in the aqueous layer, all of this right here. And then the product is going to end up in the organic layer. All right, so you're gonna, when you all this other stuff is trash. Like none of it is gonna, you're not gonna keep any of it except for that product. All right. Questions? Any questions about this reaction? We're gonna look at a bunch of them, but I just wanted to go walk you through the mechanism so that when we get down here, it becomes a little bit easier to understand. But easy is relative though, so don't panic. All right, questions about that? Oh, let me put that over here.
Dr. Russell, you don't happen to know what chapter this is in the book?
Not off the top of my head, but it is in the syllabus though.
Okay, I'll check. Thank you.
Yeah, all of the topics for organometallics, because they come from the way it's written in that Klein book. There are multiple chapters where these topics are. So I have it in the syllabus broken down based on the 3rd edition Klein book. I have it in the syllabus, like where to find these topics in each chapter. Because I think the Gilman in the 3rd edition, the Gilman reagent was like chapter 20 or 23 or something like that. And then the organometallics, the granular stuff is in a section in I think I want to say chapter 19 or something, but it's in the syllabus though.
Okay, thank you.
Mm-hmm. All right. We got 1 minute left. All right, we'll pick this up. I'm not gonna push it. I'll give you a chance to absorb what we talked about so far. We'll pick it up on Friday. Why is the dean calling me? Come on. All right, we'll pick this up on Friday. Y'all have a great day.
Thank you, you as well.
Thank you.
Hello,
Hi. I emailed you about the test.
I just finished though.